Hello, everyone. My name is Dr. Seyed Ghaffar, and I will be talking about digital fabrication of low carbon concrete for modern methods of construction. I am from Brunel University, London. We are in the west of London, very close to Heathrow Airport. And in terms of civil engineering, which is my department, we are ranked third in London, and we are amongst the top 20 universities in the United Kingdom for the engineering. And we are, of course, named after a very great British engineer, Isambard Kingdom Brunel, who made a lot of infrastructure development, and he is very well known for his key engineering solutions. A little bit about myself. I am a chartered civil engineer and a member of the Institute of Concrete Technology and also a fellow of Higher Education Academy. My main research area is material science, innovative technologies such as 3D printing. I have been the principal investigator of 8 research and development projects so far, totaling a value of £6 million, funded by Engineering and Physical Sciences Research Council, British Council, and the European Commission. Since 2017, I started a research group called AMTC, Additive Manufacturing Technology and Construction. We have had great success in terms of achieving 3D printing of low carbon concrete, and I will be talking a little bit more about it in this presentation. My external engagements include Head of Sustainable Materials and Research and Development for a startup company called Print4D, which is focused on 3D printing of building blocks. I also am acting as the expert evaluator for European Commission Horizon Europe proposals, and also have some associate editorialship in external in journals related to engineering. So today I will be talking about transformation of the construction industry, a little bit of an introduction to digital fabrication, the main topic of my research, low carbon concrete, and what it is and what we can do with it, what are the potentials of low carbon concrete, how can we, for example, 3D print with low carbon concrete. I will also discuss sustainability aspects of 3D printing in construction sector. There's a lot of questions around the life cycle assessment of these type of breakthrough technologies, innovative technologies in the construction industry. And last but not least, I will talk about my recent research on natural sand replacement with different streams of byproducts or waste. So transformation of the construction industry. I mean, the main topic here to discuss is either revolution or the transformation. Which one is it? And what is the difference between a revolution and a transformation? In my opinion, we need a transformation of the mindsets for the stakeholders, the relevant stakeholders currently involved in the construction industry, but most importantly for the new young talents, the young engineers. They need to change their mindset. They need to open their eyes to the potentials of breakthrough technologies, innovative technologies that can be implemented in the construction industry, and some of them have already been implemented in the neighboring industries. But how can we bring and transform the construction industry using these technologies to drive productivity, to drive efficiency? So revolution, in my opinion, is starting from zero. We do not really require starting from zero. We do not want to destroy everything that we had in the past century and start reinventing the wheel. We just need to transform the current practices in a way that we are using more innovation, we are using more digitized technology to transform it for better, to improve the efficiency, to drive innovation, to drive the implementation of innovative technology in the construction industry. So we need to introduce automation and digital technologies. This is a big topic. It is difficult. It's a very challenging stage that we are in terms of implementing digital technologies, but it's something that needs to happen. Inevitably, 5 years from now, 10 years from now, the construction industry's face will change. So we have to be ready for the change that are coming up. And that means the upskilling of the workforce in the construction industry, introduction of digital technologies into the curriculum, the engineering curriculum in the universities, and so on and so forth. So breakthrough technologies such as additive manufacturing, they have huge potential. Human-robot collaborations, autonomous vehicles, autonomous maintenance, and monitoring or diagnostics of the issues on site, on construction site. These are all the potential areas where digitized or new technologies can bring a lot of impact, can bring a lot of positive influence and drive the efficiency or improve the productivity that for such a long time we know is a big issue in the construction sector. The wastage of our resources, whether that is the financial or non-financial, the materials that are being wasted for the construction purposes. How can we minimize that? And that is something, the concept is construction 4.0. Some people call it a revolution, and some people, in my opinion, the better word to use is the transformation. We do not want to start from zero. We just need to transform the current practices for better. So the built environment, as we know, is facing a challenging future. As one of the major sectors, actually, we are the least digitized and automated sector compared to neighboring industries such as automotive, such as the biomedical industry. The construction sector is the least digitized and automated, and this is a very negative point to have. And we need to realize that we are behind, and we need to realize and figure out together how we can improve on that. So the built environment sector is also overwhelmed with inefficiencies, low productivities, resource wastage, as I mentioned previously, environmental issues. We are contributing to a lot of global challenges such as climate change, such as resource scarcity. And these are all, again, part of the negative points and negative impacts that our sector, the built environment sector, has on the society. Of course, I understand that it's very difficult to invest in R&D for this sector, for the construction sector, for the built environment sector, because the profit margins are very tight. And breakthrough technologies, implementation of innovative technologies, it requires a high initial capital that is very well recognized and well known. We need a high initial capital to be invested. Maybe the return on investments might be 5 years, 8 years, 10 years. So for a lot of companies, this is a difficult decision to make. And this is something that is very well recognized. The investment that is possible for R&D is minimum. And this is where we need the government, maybe. We need the universities and the government to work together in order to improve on that. The call to action of the built environment is driven by the need to become more sustainable and to evolve the way, for example, that data is used in interpretation of important decision-making processes. How can we interpret these values, these quantitative numbers, into something meaningful for the built environment and into a positive decision-making process? So it is very important for our industry to work more closely together. The competition is there, but we need to put those aside and work closely together. The collaboration here is the key. Drive the transformation. We really need to build the momentum with regards to implementation or enforcing the implementation of digital technologies or innovative technologies that are needed to minimize the impact, the negative impacts of the construction sector on our environment and the future of our society. So I just would like to discuss a little bit about digital fabrication and introduce the topic of my talk today. So what is digital fabrication? It's joining materials to make objects from a digital model, layer by layer process, deposition process. And sometimes it is useful for realizing very complex geometries. And this is where we can be quite useful to the architects and designers. This technology can be quite useful for the architects and designers in order to realize their designs and their architectural complexity that before this technology we were not able to realize. There are three important gears when it comes to 3D printing or digital fabrication. Of course, the first one is the printer, the printing environment, the pump, the flow rates, all those different parameters. The geometry is also a very important part of the gear, but in my opinion, the printable feedstock or the printable material is the biggest driving force for this technology to work. So we need to develop materials that are suitable for the printing process for the digital fabrication. So what is the exact composition of these materials, the chemical structure, the mix design, the formulation, the amounts of the water, the aggregate, the size of them. So it is a very complex piece of the puzzle, and is, in my opinion, the most important driving force for this gear, for this technology to be driven forward and slowly implemented in the sector. So I talk about these important aspects of digital fabrication quite in depth in my paper that was published in 2018, and you can access it following the link on the slide. So AMTC, what we do at AMTC, we try to combine processed organic and inorganic waste plus some additives, some clever nanofunctional materials, fibers, viscosity modifying agents. We work with a range of additives and admixtures in order to optimize a design formulation that is mainly from a processed waste, from a demolition waste, inorganic waste. And the aim is to develop these bags of cement that are suitable for 3D printing. So we call it printable feedstock. And really 3D printing is nothing futuristic. Is just a combination of different disciplines together: robot controllers, printing system, materials control, and extrusion of these materials into pre-designed complex geometries. And the main point here is to work with a material that has low carbon. So we want to also drive the sustainability inside this technology. There are plenty of companies that I have some examples to show you in the future slides that are already printing, but their main printing materials is Portland cement. And we know that Portland cement is not an environmentally friendly material. And I will explain that further into the presentation. Some of the advantages of using 3D printing is the reduction in material wastage and labor, of course. The whole production is automated, can be automated, implementing robotics printing. We have improved construction speed, no need for molds. So therefore, we are reducing the environmental footprint because we are reducing the materials used for the molds, for the form work, let's say. We have the freedom of architectural design. Multifunctionality can be easily implemented into this technology. Multifunctionality in terms of materials that we are printing. High-tech based jobs. This is a good aspect of this technology being introduced in the construction. And of course, reduce injury rates as long as you know how to deal with the robots and the issues, the health and safety issues when it comes to robots. So there are two different types when it comes to concrete printing. The first one is extrusion-based. As you can see, the illustration, we have a 3D concrete printer and a robot, and the hose are connected to a pump system. And the pump, which is connected to a mixer, is delivering the concrete, which is suitable for concrete printing. And the robot is just extruding that layer after layer. It's very suitable for on-site application, large-scale construction, and is one of the most widely used techniques for 3D concrete printing. So you have a mixer, you have a pump, and you have an extruder, and you can just build any complex shapes that you wish to have using this form of 3D printing. The next one, and these are some example of extrusion-based technology, and you can see the Cobot and Perry. There's a big collaboration between these two companies, and the materials from Lafarge. They have printed this building, as you can see in the image. And there is another one, collaboration between Cobot, and they made this complex shape, these complex geometries using the extrusion-based technique. So as I was saying, this is again General Electric's collaborating with Cobot, which is one of the biggest 3D printing companies in the world, and they have made great success out of this technique. So there are other examples of extrusion-based technology. This is actually one of my colleagues and the founder of Print4D, with whom I work very closely. They 3D printed different building blocks and they assembled it together on site in Abu Dhabi. And you can see some images and the complexity in shapes and the irregular forms that can be realized using 3D printing. So this wall is combined of 3 different segments that have been 3D printed off-site in the factory and then just assembled on-site. Different views from the same building. And these are the blocks that were printed in the factory and then assembled on-site. There is another well-known company, very famous, Apiscore, and they also use an extrusion-based technique that you can see in the images on the slide, one of the recent projects in Dubai. And some more information about them and how the project was carried out fully on site. This is different to Print 4D's technique, which is off-site and then assembly on site. This is also another valid technique that can be implemented depending on the size of the project and the requirements of the client. And this graph here, which is a very recent graph taken from a study from a paper written by Ma, is a cumulative number of large-scale 3D concrete printing projects in the construction sector since 2009. You can see that the number of 3D printing construction projects has significantly increased up until last year, 2021. And these are the range of different variety of the projects. So we have 48% houses and so on, with the infrastructure development, the bridges and steel, street furnitures that are amongst the most popular 3D printed projects. The second common method for 3D concrete printing is particle bed, which is very suitable for offsite applications, is very small scale, high precision, and you can really realize very, very complex geometries without having to worry about the conditions that you're printing in. And if things go wrong, of course, you can easily adjust it, which is in that regard is a lot more advantageous compared to extrusion-based technique. But there are some requirements when it comes to powder printing or particle bed printing. The depositability, the particle size distribution, density of the powder, and the surface of the powder quality are very important when it comes to this particle bed printing. And also the second important parameter is the pitability. So what is the setting time, the droplet penetration behavior, and how easy we can get all these droplets, these glues, the binder into these the required locations in the particle bed. Some examples of the complex shapes. D-Shape is one of the leading companies when it comes to particle bed technique. And you can see the complexity that they have achieved. Another company, Concrete 3D, and Emerging Objects is another company. And you can see that they have been able to achieve very complex geometries using this particle bed technique. So moving on to the topic of low carbon. So I talked about the transformation, the 3D printing technology, the 2 different techniques, but now the material that we need in order to use for 3D printing and slowly implement it on a large scale. All these projects that I showed you, they are very small scale and one-off demonstration projects. But how can we really have that on a large scale where all the companies are using 3D printing? And the answer for me is the material, the concrete that we are developing. And we need to develop a low carbon concrete, which is suitable for 3D printing. So therefore, I thought that is very important for me to give you some facts about concrete. It is the most used material in the construction sector. It reaches 30 billion tons annually in terms of global consumptions. And the main ingredients of the concrete is the Portland cement. And that material, the Portland cement, is responsible for nearly 8 to 9% of global greenhouse gases emission. And putting that number into context, that is equivalent of all the emissions from the aviation industry. So we talk about a huge global emission. of greenhouse gases. So we need to move away from this, and there has been a lot of efforts to replace Portland cement with alternative materials that I will go into the details in the future slides. Our modern society is facing an urgent environmental challenge. We need to reduce the CO2 emissions. We also need to reduce the waste landfilling and the depletion of raw materials. So these are the three main aspects of why I conduct the research that I am doing today in my group. We want to see how we can reduce the CO2 emission of concrete, how can we divert the waste from landfill, and how can we replace the natural resources with waste streams. And the governments have identified the built environment sector or the construction industry as one of the key sectors where there is a need for an immediate change in order to reach circular economy and sustainable development. The two main concepts that have been talked a lot about in the media, especially the circular economy, is gaining a lot of attention from the practitioners, academics, and is a new, it's not a new topic, but is a topic of interest worldwide. So how do we answer these problems? The answer to all of these emissions from the Portland cement is to use geopolymer cementitious composites. So geopolymer is made out of aluminum silicate source. We have fly ash, which is a byproduct of coal burning industry, slag, which is a byproduct of the steel manufacturing. We can use mining waste, brick powder, and etc. And as long as they have some aluminum silicate source in them, then we can activate them. We can use it to replace the Portland cement. So how do we activate them? We use alkali solutions, or we can use alkali powders. Alkali activators that are used are commonly sodium or potassium hydroxide or sodium silicates, and there are other activators that you can use. The rate of reduced CO2 emission for the geopolymer is quite varied. There are plenty of different research groups. They have done LCA, life cycle analysis on these materials, and it ranges. Some people claim that it's only 9%, some people say 45%, and there are some studies that have proved that the geopolymers can actually reduce the CO2 emission by 80%. So this is a very encouraging value, and if we can reduce the CO2 emission just by simply replacing Portland cement, and by geopolymer, that is a huge success. The advantages of these materials is that they have very high mechanical properties, so we don't have any worries when it comes to structural integrity, the robustness of the structures built using geopolymers, because they have very high mechanical capacity and performance. They have very low drying shrinkage, durability is not an issue, resistant to heat and cold, and they are also fireproof. So in the image below, you can see that it's very simply combination of aggregates, fine, coarse, with water, activators that are typically in the form of liquid activators, but there is now solid activators, a simpler way of making geopolymers. And you can combine it with GGBS, which is the slag, and pulverized fly ash or fuel ash, and then you get your geopolymer concrete. Within geopolymer field, there is now a move to a one part just add water mixes. And as I just simply said in the previous slide, you just replace the activator, which in a liquid form, and you use the powder. So it's a lot more easier. You do not have to worry about the hazards of these alkaline solutions being handled on site by the laborers. Obviously, they are very extremely dangerous. And there is no tear and wear issues with the parts and the mechanical parts in the mixer or the 3D printer. You just use the powder form of these activators, sodium silicate, and you add water. So it's a lot more scalable. The scalability is not an issue, and it's very simple. And at the same time, it's still very sustainable. So you just use a powder activator instead of a liquid activator, a solution. So let's talk about 3D printing of these materials, these geopolymers or low carbon concretes. We've done a lot of tests in our lab. We started very small scale. We use extrusion-based technology. So we have a gantry system. There is a nozzle, a control unit, and an extruder system, and you can just about see our pump delivery system. So the material is fed into the hopper. There is a screw inside, and the material gets extruded to any shape according to the CAD design. So I have some videos showcasing some of our early trials with Portland cement in order to have a benchmark in terms of printability, to see how we can achieve what type of strength we can achieve, and if we can outperform Portland cement based mixed formulations using geopolymers, using low carbon techniques. And you can see some of the pictures of the objects that we were able to 3D print as a benchmark to the new material, for the new material which we have developed, geopolymers. And this slide here really shows the potential of geopolymers. You can immediately see that the quality of the print is a lot more high resolution, and mechanically I can report that the results are also very good and up to a good standard, and they actually do outperform the Portland cement mixes. So you can see in this video, the resolution between the layers, the quality of the print is very good. There is no issue with the printability, the extrusion, and the layer height. The buildability is actually quite good. And we can achieve very complex geometries using this technique by this material, geopolymers. So I have reported all of these formulations open access in our journals, and we investigated different binders, fly ash, slag, and silica fume. We had some additives, PVA fibers, and some nanoclays, and all of these formulations are reported open access for everyone interested in replicating our results or using these mixed formulations to build on their own developments. This was our testing program. We had additives, we had matrices, different samples were made. We tested their fresh properties and also when they were 3D printed and casted in order to draw some comparison. We evaluated their microstructure, the mechanical properties, and added some additives to the best performing ones, the best performing samples. After the additives addition, such as PVA fibers and anthropologite nanocray, we carried out another set of testing, flowability test, mini-slump test, rheology, extrusion window, and so on. So these are the mechanical results along with the density. The green bars are representing the printed samples, and the orange ones are representing the cast samples. And you can see that we were able to get very high flexural strength, as high as 14 MPa after 7 days of printing or casting. And the compressive strength was actually quite high after 7 days, up to 70 MPa. So this value compared to Portland cement system or Portland cement mixes is a lot higher, and it outperforms the Portland cement, as well as being low environmentally impact mixed formulation. And I have some microstructure analysis here. We used some PVA, and the PVA was a crack blocking or crack bridging mechanism that allowed us to achieve very high flexural strength, very high tensile strength, which is commonly known as a weakness when it comes to concrete materials, cementitious materials. So moving on to sustainability and life cycle assessment of the 3D printing, there are a couple of points that I would like to share with you. So the best way to tackle this topic is to show you some graphs, some analysis on the CO2 emissions and the embodied energy of a 3D printed geopolymer mixture compared to a 3D printed Portland cement mixture. And you can see that the OPC is the one that has the highest carbon dioxide emissions per kilogram or liter of the material used for 3D printing. Whereas in the geopolymer, the highest contribution comes from the solid activators, not from the slag or not from the fly ash, because these are byproducts of other industries. And when it comes to embodied energy, you can see that the 3D printable geopolymer again outperforms the OPC mixture. But in this case, the difference is not that much, is not as much as the case for carbon dioxide emission. In terms of embodied energy, for 1 liter or in terms of millijoule per liter, we have 1.6, whereas ordinary Portland cement is 1.8. And the biggest contributor for geopolymer is, again, solid activators, but for OPC system is the Portland cement. So when it comes to LCA, there are different considerations to be made. The environmental impact of concrete used for 3D printing is focused on cement, and we need to replace the cement. This was something that I mentioned before. We can use alternative materials such as limestone, calcined clay, fly ash, and slag, which can considerably decrease the environmental impact. But we also need to know that the 3D printing advantages, we can have more complex geometries, and we can have multifunctional structures, which tends to benefit the environmental performance a lot more compared to conventional construction methods. And also, there is some doubts when it comes to robots and equipments in terms of their actual significant influence on the LCA. I mean, we don't yet know, we don't have a clear idea about the actual impact of robots or equipment used for 3D printing process. And this is something that has to be studied in the future in order to get a very solid answer when it comes to comparing the life cycle analysis of a conventional method of casting, for example, of a concrete mix and 3D printing it. The next point to consider is that most of the research use cradle-to-cradle boundaries, and they do not really focus on the degradation of the 3D printed materials and the durability of these materials. So we need to really be humble about the technology. We really need to consider the cradle-to-cradle boundaries instead of the cradle-to-gate. And this information could be very fundamental to predicting the service life and end of life of the printed structures. What can we actually do when the printed object comes to the end of its life? Can we recover resources, for example, from it? And most of the recent papers about the life cycle analysis for 3D printing use different size of equipment, different printing scale, and this really makes it very difficult to judge what is really and truly the best method of producing a concrete block. Is it 3D printing or is it the conventional ones? Having said all of these, this is to mention that we really need to be humble about the technology that we are talking about. There is still plenty of considerations to be made, plenty of investigations to be made in order to prove that this technology is not only a fairy tale story and can have a positive environmental impact. I mean, I talked about the advantages, but the topic that I'm discussing here now is the low carbon. Is it really and truly a low carbon? I talked about the low carbon material for printing, but how about the process? Is the process of 3D printing any good in terms of the life cycle analysis compared to conventional methods? So there is still a lot of unknown and a lot of research to be done, a lot of research to be conducted in order to be able to draw conclusions. The last topic that I would like to cover is the natural sand replacements. And in my research groups, we have worked with PVC, polyvinyl chloride, which is coming from the covers of the cables. We try to see if we can recycle some of them in the cementitious composite into low carbon concrete. We work with rubber from tire rubbers of the heavy vehicles, glass. There's been a lot of study on base glass, and also bricks, the clay bricks, which has shown actually to have a very good potential as a replacement of sand, as a replacement of a natural aggregate inside the concrete, inside the mortar or concrete. So some of the results, we worked with alkali activated materials or low carbon materials. Some people call it polymer. We had slag from the steel manufacturing, silica sand and fly ash as our binders. And the aggregates that we used were obviously natural sand for benchmarking purposes, PVC and rubber. We made different replacement ratios, 30% PVC replacement, 30% rubber, 50 and also 70%. And we assessed quite comprehensively different parameters, different performance criteria in order to see if the PVC and rubber have the potential to be replacing natural sand. So this is the microstructure of the PVC, and B is the microstructure of rubber. You can see that there have some smooth surfaces, and some of them has very rough surfaces. There are some sharp edges inside them, and all of these could be beneficial when it comes to mechanical entanglement with the surrounding binder. And that could be really detrimental for the mechanical properties, for the durability properties of the end product, of the end concrete, the resultant concrete. So this graph here shows the flexural strength. Of course, as expected, the addition of waste aggregate actually dropped the strength for flexural strength in the case of flexural strength and compressive strength. And you can see that the 70% replacement of the natural sand with PVC or rubber has actually achieved the lowest mechanical properties. But the point here is that 30% replacement is adequate in terms of mechanical strength. And we can actually, for non-structural load-bearing applications, we can replace up to 30% or even 50% of the sand with recycled materials if the application that we are designing for is a non-load-bearing application, is a non-structural or semi-load-bearing applications. Because for example, for compressive strength, at 30% replacement of natural sand, we were able to get around 30 to 40 MPa, which is still a respectable value for non-structural load-bearing applications. And here again is a microstructure of the material then broken in half after the testing, after the mechanical testing. And you can see that the interfacial zone between the PVC particle and the matrix, low carbon matrix alkaline activated materials is actually quite strong. And there is a very good interfacial bond between them. In the case of rubber also is less so when it comes to interfacial bonding quality. There are some delaminations. So this shows that the rubber is not the best option when it comes to bonding quality and interfacial bond between the cement binder and the aggregates. So therefore, the mechanical properties are a lot lower. One of the most important figures here is actually the replacement percentages and the equivalent CO2 emission. For the control sample is 230 kilograms CO2 per ton of the material. But for 30% replacement with PVC or rubber, you can see that is considerably lower. For 50% is a lot lower. And we found that for 70% replacement is actually negative. So because we are using a waste-driven product to replace the natural sand in the case of PVC and in the rubber. So these results are very encouraging, showing that if we want to develop something sustainable for a non-structural load-bearing application, we can actually use 70% of these PVC or rubber to replace the natural aggregates. And as I said, the natural resources are depleting, and we really need to reserve them. We need to be careful when we design a concrete block which is not for structural load-bearing applications. We can use recycled sands, recycled aggregates, such as PVC and rubber. So the main key takeaway message from my presentation is that the creative ideas are really needed to reduce the waste from the construction sector, and we really need to save the Earth's natural resources and deliver net zero carbon construction. So I really thank you for your attention, and I'll be happy to answer any questions.